So yeah, during today's lecture, we will try to go through variational and autoencoders in general, all of their variations, hopefully. And then we will speak a little bit about segmentation, what it is and its different types. And of course, we will focus on majority of the time, we will be speaking about UNet and mask RCNN. UNet mainly because it's still very much used in major models such as, the DALL-E or the latest diffusion models that are like generating images. So it could be something that in the future might completely replace scans. So that's why we're going to spend a lot of time explaining the architecture. And then we will go to the mask RCNN, which is just like the continuation of the RCNN family or the latest version of the RCNN family. I'm not sure if we will have a lab next week about segmentation. Only thing that I wanted to show was the theory behind autoencoders so that you can start doing the projects. But if the students also need a lab for it and just to see how the code works, then we could certainly have a lab about segmentation in general. And then maybe a little bit of a lab about diffusion models and how they work and how you can train them very, very simply. They're pretty simple models, so I think it's not going to be that difficult. We're not going to train big one. We're just going to train like a small, teeny tiny one. So yeah, so the goal of this lecture, as I said, was to understand the concept of latent space. What is a latent space, right? Why do we need such concepts? What is an autoencoder? All of these questions. These are very important questions for at least the project that you guys will be doing, because you will be manipulating a little bit of these features or latent spaces that the neural network will extract. So one of the projects, for example, was a facial recognition software or algorithm. And basically for the facial recognition algorithm, what you will be doing is you will take an image of a certain face. So the first face of, let's take G, for example, you take the face of G before he started studying. And then every time he goes to the classroom, you compare the new face or the faces of the students against the database version of the face of G. And how you do this comparison is by taking the face of G in the first time and putting it through a deep learning feature extractor that will extract the latent space. And then you compare that latent space to the same thing, the latent spaces of each individual face in your classroom. And the one that is the closest in terms of latent space to the original face of G, that is what we will consider the face of G in the classroom. So that will be able to allow us to understand where G is in the classroom or in the university. And this is something that is very commonly used, especially, for example, in China or something. It's controversial, but it's still very important for you as as engineers in the field of deep learning to master and understand very well. So previously, in the terms of feature extraction in, I don't know, I think before 2012, everything between the 1980s till 2010 and stuff, a feature extraction process from images was done manually. So I'm not sure if you guys will have the course of computer vision, and hopefully you will. It's a very simple course that is provided usually to the master students and to the data science students. And in this course, you will see the different techniques that we use for computer vision to extract features from images, right? So this feature extraction is usually, again, based on the concept of convolutional neural networks, or just the convolutional operation itself. But instead of having backpropagation train the weights, we have fixed weights that are handcrafted. So basically, human experts would come and set each individual value for the convolutional filters by hand for specific data sets. So they will have the weights for the convolutional operation for the cars, the weights they will have something for, I don't know, for faces, human faces, etc. So each one of these faces or each one of these feature extractors, these convolutional feature extractors were trained or fine-tuned by hand. Whereas for deep learning process, or in the deep learning world, feature extraction and the classification are both a training approach. They're both being learned, right? So there's no human expert that comes in and says the best convolutional weights for a car are 2, 3, 4, 5, 6. right? So this part where we set the convolutional weights is being trained from scratch. So either basically from scratch or using transfer learning, but it is something that we train individually for each data set. Autoencoders is also the concept that we would like to learn basically the most in this, what is it called? In today's lecture, mainly because it's highly related to what you guys will be working on, whether be it diffusion models for some students, or for the other students who are working on like facial recognition, then definitely at least the first part of the autoencoders is extremely important to learn. So an autoencoder is a very simple feed-forward neural network, similar to basic CNNs, similar to multi-layer perceptrons. It's just a neural network that takes input and maps it directly towards an output. There is no recursive operations. There is no something like RNNs, similar to the natural language processing trainings. This is a very straightforward approach to training a neural network. And it starts by doing the first approach doing the first part of the training, which is projecting the input to an encoded space. So the encoded space or the latent space or the code, these are multiple words that you might see in research papers a lot that are describing, well, let's go back again to facial recognition or to the part of diffusion models or even like transfer learning or even domain adaptation. So you'll find these terms being used extremely heavily in research papers, and all that represents is a vector space that learns information or heavy information about the input image. So the information that is in here, it's just basically the convolutional feature map. Remember the convolutional feature map? This is just a CNN, a basic CNN, and this is the convolutional feature map, the output of that CNN. Now, what makes this output extremely important? Absolutely nothing, right? So here in the encoder, we will have multiple layers, right, of CNN layers, convolutional layers, right? And for a specific reason, we will be taking the final layer as the code of the image. Why? Just because we defined it, right? So if you want, you can take this as the code or this output of the fourth layer as the code. All of them are potential codes, but the best code to use is usually the one that comes after the last fully connected layer. So after the last fully connected layer, this is, let's say, after the last convolutional layer. After the last convolutional layer, you will be extracting, in theory, the most abstract or the most useful or the most high-level feature encoded from that image. So what ends up happening is the following. The encoder is just a couple of convolutional layers, and we define the end of the encoder as the end of these convolutional layers. These convolutional layers will give us a convolutional feature map. That convolutional feature map, as we have seen, has lots of different locations that are like activated, right? Those activations mean that the convolutional neural network has found something useful in that location in the image, going back to, for example, GradCam and how we interpret that convolutional feature map. So here we see that we have a way to understand what are the different locations in the image that are important to the classification or that are important to the training task in general. So this code that comes out of the encoder, that convolutional feature map, if you will, or the vector representation of it, are just a highly condensed or highly abstract representation of the input image. And that's what makes it extremely useful, right? Because if you have a representation of the image that is a vector form, like this in a vector form, right, where you have individual features, That means everything you have learned, for example, in linear algebra is applicable. Things like just calculating the difference between this vector and another vector. This can give you the difference between, or the difference between these two vectors. So instead of calculating basically the difference between an image of face of student 1 and face of student 2, what we can do is calculate the difference between their latent representations. Because these latent representations are more useful, are usually much smaller, and they contain much more important information than just the image itself. Because the image, sometimes it has, some background noise. It might have like the eyes in image 1 are here, but the eyes in image 1 are here. So you have lots of problems in the image, but once you go to the latent space, everything becomes more stable and it becomes more comparable using things like basic subtraction becomes very important and becomes very useful, and in this vector form latent space. Now, the second part of the autoencoder is the decoder, right? So the decoder is the absolute opposite of the encoder. The encoder takes an input image and outputs a code or a latent representation of that input image, whereas the decoder does the exact opposite. Mainly, it takes the latent code and outputs the exact input image. So the first thing you will notice about this architecture is that it is unsupervised, right? Yes, we do have an output. We do have the classification loss in here or the regression loss. It depends how you want to implement it. So basically, this will have just typical regression loss, pixel by pixel. We compare the values. If there is a big difference, then the MSE will go high. If there is no difference, the MSE is low, right? So this one is basic supervised learning, but there is no labels, right? So it is normal classification, just like any other architecture that you have seen in the field of supervised learning. But the problem is there are no classes. Hence, this is unsupervised learning. So these autoencoders are a form of unsupervised learning, mainly because they're trying to predict the input itself. There is no external class to the input that is guiding the training or something like that. We're guiding the training through the data itself. So again, just to recap, input, an encoder, which is just a simple CNN, and then outputs a convolutional feature map or a code or a latent space or an encoded space. All of these are just the same, different names for the same concept. You already understand the concept of a convolutional feature map or an activation feature map, right? This is the exact code that we spoke about, which is something that is extremely useful because it contains higher level information about the image, regardless of their location. For example, as we said, if you have the eyes at this location or you have the eyes in this location, hopefully the activation feature map, once it is, passed through a lot of max pooling layers and a lot of convolutional layers, will have a more uniform representation in this vectorized code form. Now, the decoder architecture, we will not go too much in depth into it, but if you remember the YOLO, right, we did something that is called upscaling, right? So in YOLO, we did this concept of upscaling. We discussed what it does, right? We said if you have just a simple image with, like, let's say the first pixel was 1 and the second pixel was 20, you can make this image like much bigger by saying first pixel is 1, and you just put some random pixels in the middle. Let's say we're just going to put 3 pixels here. And there you go. So you just converted a small image of 2 by 2 into a bigger image of 5 by 5. All you did was impute the values in the middle using just a linear transformation. So it's a very simple technique, the upscaling technique. And how it is used here in the decoders, simply we take this convolutional feature map, we upscale it by twice, and then we send it through a convolutional layer. So basically the decoder is very simple concept. What it does is takes an input convolutional feature map, upscales it, and then send it through the convolution. So it's very similar to an encoder, but before every every convolutional layer, we have an upsampling layer. So what happens, what ends up happening here is the encoder will take an image that is big, outputs a latent space that is small, and the decoder will take a small latent space and upscale it into a big output image of the same size as the input.
Excuse me.
Yes.
Okay. Can you hear me clearly first? Technical check. Can you hear me?
Yes, perfectly. Yep.
Okay. So as a I'm not sure about the decoder part because it seems like a very oversimplification thing. Because, for example, what I see is the latent space should be somehow more uniform across, for example, the face structure, right?
Mm-hmm.
For example, if we want to do some face recognition, or let's say even image classification.
Yes.
So the latent space would be somehow, I don't know, like having an edge at the upper part of the image, something more abstract.
Yes.
And I don't see how upscaling, because the upscaling procedure that we just described is very uniform in a sense.
Yes.
So we're going from uniform abstraction using a uniform procedure. It doesn't seem to me how it's possible to go to a particular result, if you got what I mean.
Absolutely. So what ends up happening is the upscaling, it's a stupid operation that has no learning, right? So upscaling has no learning, has no parameters, has nothing. It's just a stupid operation, takes in a couple of numbers and just puts more numbers as output, basically just through a line between those pixels. So the upscaling is a very stupid operation. But what comes after the upscaling is the convolutional operation, which is a learning operation, right? So what ends up happening is your model or the decoder will learn some parameters that are useful to convert the latent space into the input image. Does that make sense?
Processing, loading, one second.
Yes, so the same way that the convolutional feature map, the input here, right? The input here is able, or the encoder in here is able to take an image like this and extract a code or latent space that contains higher level information about the image. We're going to do the exact same thing, but taking this higher level code and converting it into an image using the exact same power, which is the convolutional operation. But the only difference is we will just make it bigger. Make sense?
Oh, no, because now, as you mentioned this particular part, I'm trying to remember the fact that, for example, when I studied convolutional neural network, first, how it was introduced is that, for example, at least in the very beginning, they didn't use parameters in convolutional network. They were actually trying some very specific values. For example, some I don't know, some kernel that is used to modify to detect, for example, edges. That's what I remember. And now, when I think of it, it's like, as long as we can detect, for example, as long as we have some kind of pattern that detect edges, it doesn't seem impossible to revert it in a way. And that's what probably the convolutional part is doing. But I probably might get some more idea if I can read more about it. I guess
so what the convolutional operation in its core is just a basic linear combination followed by a nonlinear activation, right? So it's just the basic sum and multiplication with some values, and then you follow it by a simple nonlinear activation. That's all, right? That's all it is. The power of it is the fact that it's trainable, right? So it could be trained to do absolutely anything. Now this, we will see later on, for example, in the denoising autoencoders, how can we use this noisy image and go to a non-noisy image, right? So just through the power of learning. So this is what makes it interesting is you will take the input and you will try to learn from the input itself, from the data itself, what makes the data the data. So in here, your code or your encoder is being trained on a loss function, and the loss function is defined through the values of the decoder. So your encoder is trying to generate a code that is easy to use by the decoder to regenerate the image. So in this case, the encoder and the decoder are working together to build a code or a latent space that, first of all, summarizes as much information from the input as possible and is useful for the reconstruction of the image. As you can see in here, it's not perfect. It's not like 100% reconstructed, but it does contain some of the information from the image, right? You see?
Yes, I have just got the question. If do we train the encoder and decoder in the same together, like in the
Yes,
same goal?
absolutely together. Both are being trained for the same objective or the same loss function. As I said, the loss function is a very simple loss function. It's basically the input minus the output, or the predicted output minus the input, to the square root. That's it. So it's just like you are, imagine instead of predicting the input image or predicting an image, all you are predicting is the temperature or the age, the temperature. You're predicting a number 50. And the actual number was 56. So your loss function is 50 minus 65 to the power of 2. This is your loss function. Very basic loss function, MSE. This is what the model is using to train, right? And that is the loss function that trains both the encoder and the decoder. Make sense?
Yes, yes, yeah, I'll say it.
Don't worry, we will see a little bit more. So what the encoder ends up kind of doing, not exactly doing, but kind of doing, is it will take an image and it will encode it to higher level features that can be used by the decoder to reconstruct the same input image. Now here we're simplifying to make it something that humans understand, but the higher level features that the encoder is learning are definitely not as simple as this, right? So here, for example, we're saying he is smiling, or smile equals 0.999. Skin tone, 0.85. Gender, minus 0.73. He's not going to be learning these concepts, but he's going to be learning concepts that are useful for him, right? So concepts that the computer model is able to understand and interpret. These are concepts that we can understand, and just to simplify your understanding, but the actual understanding of the model is in most cases very, how do you say it? Much deeper or more complicated than that. So there were some tries to explain that by saying, for example, the hair color is dependent on on the value, the first value, the third, and the fifth in the latent space, for example. And then the smile is encoded in the second value of the encoder, and then in the -2 or something like that value in here. So they try to basically see what the model is actually learning, but in most cases, it's not easily humanly interpretable. These are just some latent attributes that the computer vision model is able to understand, but not as humans can understand. But just for an example, what we're saying here is an image encoder, some latent information, for example, like this, right? Just a small description of the image that can be used by the decoder to reconstruct the same image. So here we see, again, the components of the, what is it called? Of the autoencoder. As we said, encoder, decoder goes from input to a very small code. This is why we expect this code to be condensed representation of the input image, to be a representation that is very high level and contains as much useful information as possible about the input image without having too many details in there. Application areas are endless. For example, just zipping the folders. For you take, for example, here a big image and you represent it or you save it in your laptop as just a much smaller code. And if you want to see the image, all you have to do is take the code and put it through the output, and you will have some sort of an almost similar image to your input, but instead of putting it as 20 megabytes, you only put a couple of kilobytes, right? So these are some of the applications of the autoencoders, but the applications that we want you guys to do are precisely working on diffusion models and working on facial recognition models. So these are like the two most applications that I've seen in the projects, and this is why we're trying to explain them. So just to recap, the encoder creates a hidden layer containing code to describe the input, whereas the decoder reconstructs the input from that hidden layer. A very big concept in the field of computer vision is denoising autoencoders, which is an autoencoder that takes noisy input. This is just Gaussian noise, right? So you take the image, you put some Gaussian noise, and you put it through the encoder, get some compressed representation, get some latent representation, get some code how do you say it? Just so, yeah, encoded space. A lot of words can be used to describe this representation, right? So again, in many research papers, it's described in a different way. It depends on how they call the encoder. Sometimes it's just the CNN part of the classifier. Sometimes it's the encoder. It depends on what they call it and how they call this latent representation. Some people represent it with T, some people represent it with a Z. Z is most common, but it depends, right? So this compressed representation is later sent into a decoder, but the decoder is being trained to generate the denoised image. So it's not generating the input of the encoder, it's generating, sorry, no, okay. So imagine the following process. We take a 2, apply some noise to it. So it becomes 2 with some noise. Encoder learns a representation of this image, of this noisy image. The decoder decodes the original 2. So the encoder takes in this noisy image, whereas the decoder, this is a Z, no? Not 2, Z. Yes. So the encoder takes a very noisy version of the 2, goes into a latent space. The latent space is decoded by the decoder into a beautiful, clean version of a 2. So this is the, what are they called? The Y hat and the Y, right? So basically, encoder is a function. Let me just write it. So encoder is a function that takes X noisy. And the decoder is a function that takes Z, right? The decoder is later on trained on a loss function. So loss is equal to MSE between, let's say, predicted X predicted, comma, the actual X. Make sense?
So we assume we have the original non-noisy
Yes,
picture,
yep.
right?
Yep. So
Okay,
here, before we do it, we do X noisy is equal to noise Gaussian of normal X. So this is something that is an operation that we can do, just adding random pixels. That's it. Very simple operation. You don't need neural networks, just basic math, Python, right? Now the decoder here, this is X spread, the output of it. And this is Z. Z is equal to this. There you go. This is the code for the denoising autoencoder. This is literal code that you will write in Python, right? This is what you will be writing. Just 4 steps, very simple steps. The encoder is a very simple function. The decoder is also a very simple function. MSE is very simple loss function that you already have implemented by PyTorch. And there you go, loss dot backwards. Sorry. And then whatever the name of your optimizer. So let's say opt dot step. Yep. So this one calculates the back propagation loss. And then this one, or back propagates the what are they called? The gradients, yeah. Back propagates the gradients of the loss to the individual weights. And this one takes one direction in the one step in the direction of the optimization, right? That's it, based on the learning rate. So it's a very simple concept, the concept of autoencoders, right? It's a very simple, direct concept that just builds on what you have already learned in the field of, honestly, in the first lecture, right? We have seen already what convolutional layers are. The only difference in the decoder here is to look at the concept of upsampling. Upsampling, again, is not a big layer or a very difficult layer. It's just a basic Python function that takes in a couple of numbers and puts out more numbers based on those, right? Just from 1 to 20, it just puts in like a line between that 1 and 20, makes the image a bit bigger. Now, there are multiple types of autoencoders, right? So there is the first type, which is under complete autoencoder. This is the type that you will be seeing in the majority of your life. There are over complete autoencoders, which are quite useless, but they're still useful to, or they're worth it to talk about, because there are some applications that require an over complete autoencoder. Usually these over complete autoencoders are sparse autoencoders. And again, there are the denoising autoencoders, which are the most important application of autoencoders, mainly, especially for those who are going to diffusion models or going to do their project on diffusion models. Diffusion models are just denoising autoencoders on steroids, right? So here, we said we put a little bit of noise into the input image and we ask the model to denoise it. Instead of doing this once, for the, what are they called? For the diffusion models, what they do is they do this 1,000 times, right? So they take this noisy input image and they try to denoise it. And then what do? They consider this as the actual good image and they put extra noise in it. So here what they do is they take the input image, they put some noise once, and this gives you noisy image 1. Take noisy image 1 and put even more noise on it. That gives you noisy image 2. Take noisy image 2 and put even more noise on it. That gives you noisy image 3. And repeat this process until you arrive to noisy image version 1000. Noisy image version 1000 is most likely going to be just pure noise, just absolute nothingness, an absolutely noisy image. And then what they do is, step by step, they go from X1000 to predict the version that is right before it, X999. And then they repeat until they try to predict X1 hat, or the denoised version of X1. And then from that, they will try to represent X hat, which is the actual image that you will see. So the diffusion models, or what you see, for example, in DALL-E or Imagine, all of these new models are basic autoencoders or denoising autoencoders that are put on extreme steroids, right? They are just trained very hardcore. Instead of doing it just once, right? Here, this is the, let me just type it. This is denoising autoencoder. Do this operation 1,000 times and you get yourself a diffusion model, right? So this is it. We will see how to code basically a, what is it called? A denoising autoencoder. We will also see how to code a diffusion model, a teeny tiny diffusion model, not the big one. But in reality, they are very simple models, but they require a ginormous amount of training and a very big amount of or time to basically do the learning process of these images, right? So now let's go to the most important type of autoencoders, which are variational autoencoders. A simple question right now: did you guys study variational autoencoders already?
It's my first encounter, I would say.
Okay, that's a bit bad. I expected you guys did. So variational autoencoders are just an autoencoder, but instead of predicting a latent space that is just a vector like this, basically this vector is very simple. Huh? You remember the convolutional feature map? We flatten it. So this is what this vector looks like. This is why you see a one-dimensional vector. It's just the convolutional feature map that is the output of a convolutional layer converted into a vector space. So the autoencoder predicts a encoded representation that is like this, just one-dimensional vector. But the variational autoencoder does not give you an absolute value. It gives you a distribution, right? How do you define a distribution? For example, a normal distribution, you need two values. First value is the mean. The second value is
Variance.
standard deviation or the variance, as you wish. So this is the representation of a value or a distribution in the variational autoencoder. So instead of having one-dimensional vector, you will have two of them. Very simple, right? The first one is the mean. The second one is the variance. And there you go. Instead, just by predicting two vectors, right? Just by predicting two vectors, you're able to get to, what are they called? Just one big distribution instead of having just one value. Now, the major differences in here, I will not really go into the training of them because the training is very, like the loss functions here are completely different and lots of changes happen. So probably you will study this in the advanced machine learning course. I'm not sure if I will be teaching it or somebody else will be teaching it, but it's going to be like a very simple loss function that is based on just pure probabilities, right? It's just based on probabilities. It's simple. And you will see, for example, concepts as sampling in here, right? So the sampling operation, this is just a Python operation, but at the same time, you would like to do a loss function that is differentiable from here to here. And so you will need to learn some tricks into how to convert this sampling operation from a Python operation that is not differentiable into something that is extremely differentiable based on the means and the variances that we have here. But for the sake of this lecture, just understanding the concept of a latent space, you really don't need to know, KL divergence and all of these different loss functions, at least for now. Maybe if you want, we could have a future lecture about GANs and training a probabilistic model in the future, or maybe probably after we do the natural language processing part of the course. But very simply put, this is the difference between a variational autoencoder's latent space and the autoencoder's latent space. So for example, here the child is not smiling, right? So smile is a negative value. This is the latent space. Here it gives you, in the autoencoder, it gives you one value for the smile. Whereas in the variational autoencoder, it gives you a distribution of where that smile could be, right? Yes, it could be the same here, right? And the mean is usually exactly what the output of the autoencoder is, but the standard deviation is just going to put some variety in the output, right? And that's going to help us create a much smoother latent space, a much more useful latent space for the reconstruction, because it's very smooth, right? That's what we want. If you have a latent space of, I don't know, let me just type, let's say 5, 6, 8, and 9, and you have another latent space of 5, 6, 8, and 9.1, you want the decoded versions of these two images to be similar to each other. In the autoencoder, that's not always the case. In the variational autoencoder, that is kind of enforced by the loss function itself. And that's what makes it a bit more useful, at least, right? The variational autoencoder, the ability to predict instead of just one value, and then it gets mapped into the image or decoded into the image. Now we're predicting a distribution. And from this distribution, we can sample as many times and go to that same output image. This allows you to leverage the training data set a lot more or a lot better, right? So instead of one image giving you one latent space and then one decoder iteration, one image gives you hundreds of latent spaces because you can sample as many times from these different distributions as you want. And each one of those samples will be a little bit different. It's not going to be fully different, a little bit different, just a little bit different, enough for the decoder to actually give you the same image, but the same image from different latent representations, which leads to a much smoother latent space and much better decodings and hopefully generations, right? So if you can use this method to decode the input image, can you use the same thing to generate a new image? Absolutely. You just put some random numbers here in the smile probability. You put something smiling, you put something here, you put something here, you put something here for the skin color. You just do some random numbers, and then from those random numbers, you can use the decoder to actually generate an actual new image. So this is what happens in the variational autoencoder. Takes an image, sends it through the encoder. The encoder now is not generating one value for each latent space or latent space attribute. It is now generating a probability distribution based on the mean and a certain standard deviation. As you can see, the standard deviations are not the same for everything. Each value has its own standard deviation, and each value has its own mean. And then the decoder will try to decode a sample from this. So we take the encoder. Here's the encoder. We sample once, we get this. We sample another time, we get another latent space, and then we decode them into the same image. So we expect an accurate reconstruction for any sample from the latent space here that we get here. That leads to, as I said, a much smoother latent space and better reconstructions in general. So right now what you're doing is you're kind of leveraging more data than you have in your data set just by adding some randomization to your process. Now, before we go forward and speak about segmentation part of this lecture is going to be quite simple. We will speak a little bit about UNet in depth, but the rest we're going to go through them very quickly. And then we'll speak a little bit about mask RCNN, which is also a very simple concept since you've already done the faster RCNN. Let's just take a 5-minute break and we come back. Prepare some questions during this 5-minute break. So I would like to get some of your questions about the concepts that we have seen so far. Concepts like latent spaces, concepts like encoder, decoder, autoencoders, variational autoencoders. If you have some questions about diffusion models, any of these questions, please, they are welcomed, especially if they are related to your project. So the second half of the course is going to be tailored to your projects. If you have any questions that you would like to see in the future, we can definitely change the future part of the course to fit questions specifically for your projects, okay? See you guys in 5 minutes. Resume. Yeah. So do you have any questions so far about everything we have seen? So variational autoencoders, latent spaces, maybe somebody wants to know how we can use latent spaces to to detect human faces or to recognize human faces. All good? Okay, all good. So let's go to the second part of this lecture, which is the segmentation part. And this is a part that is going to be heavily like influencing your grade in the final quiz, right? So it's gonna be a very big and important part of the final quiz, mainly because it's very simple to ask questions about it, right? So when it comes to like latent spaces and autoencoders, definitely they're going to be part of the quiz, but this one is much more simpler for me, at least, to make hundreds of different questions about, and the questions are always very interesting, at least, right? So for segmentation, it's very important to understand that there are multiple types of segmentation, and these are not the only types of segmentation. There are hundreds of other types of not hundreds, but lots of other types of segmentations. But these are the most commonly used types of segmentation, and they are very important because they kind of split the architectures of segmentation models in the industry. So the first type of segmentation is called semantic segmentation. And you already can see that, for example, the other part, which is instance segmentation, you have a lot more colors. But the semantic segmentation, you just have two colors. And if you look even deeper, you will see that all of these humans in semantic segmentations have the same color, whereas here, all of these different humans have different colors. That's the only difference between semantic segmentation and instance segmentation. Basically, in semantic segmentation, we don't care about the objects themselves. We just care about what is the class of this pixel. So for example, this pixel belongs to a person. This pixel also belongs to a person. We don't care that they are different people. We just want to understand where is the class person located inside the image. That's all we care about. Where is the class table inside the image? Whereas for instance segmentation, we care each object where it is, and for each object, what is its mask. So here, for example, we have person number 1, this is his mask. Person number 2, this is his mask. Person number 3, person number 4, 5, and 6. And then we have table number 1. If we had another table, it will be here also with its own color, meaning it is completely separate from this object. A very basic understanding of autoencoders will help us see that we can use them to do exactly this, right? So what we can do is, for the sake of semantic segmentation, what we can do is we take an image, input image like this, and manually human beings will annotate basically this class or this pixel map, or what are they called? Yeah, let's just call it the pixel map, or a mask of the image, where basically we try to take the input image and learn an encoder and a decoder that can find the locations of these interest classes, right? So for example, here we have n classes. If for some reason we had a cat in here, here's a cat, this is how cat looks like. In the pixel map in here, you will also see the cat. Now, the first question is, why is this n existing in here? We can have everything in the same, in the same channel, and that will speed things up, right? But the problem is, as we have seen before, we're not just interested in finding, basic segmentation that is foreground versus background. We're interested to find background versus each individual class. So what ends up happening is the background gets ignored. So all of this blackness in here is just background, which is ignored. And each individual class will have its own mask, or will have its own pixel map. How do we represent that? So when you have lots of masks, which are just matrices, right? When you have lots of matrices of the same size, what you can do is merge them in the same representation, and each individual matrix will be a different channel for this this mask in here. So we will have a mask instead of 224 by 3, which is the RGB image, you will have 224 by n, which is the number of classes. And then, of course, the encoder and the decoder will try to predict this output shape to reconstruct the locations of the images. This is a very simple, simple segmentation model. Clearly, it's very difficult to make the annotations. So you have probably seen already during your work on the homework how much time it takes to create just a simple basic rectangle over the object. Now you can imagine how much time it takes to create this map for each class in each image. So it takes a lot more time. It's a much bigger investment in terms of time, but the results in performances are usually also better, right? So what ends up happening is you're giving the model much more detailed information, a much more rich loss function. And what ends up happening is the back propagation of the gradients of that rich loss function ends up training much better weights that give you very good segmentation models. So it's a very simple task. You take the input image and take the output image that you want to predict, and you train a learn a autoencoder that does that task for you. Very simple task, very basic representation, no major changes in here, but something that you could keep in mind as a potential architecture for, or potential use case for autoencoders. Now we improve on that, right? So instead of having an autoencoder which can or cannot have convolutional networks and fully connected layers, so what ends up happening is this new architecture that is called fully convolutional neural networks is exactly like that. So it's an exact replica of encoder and decoder, but it just has one simple extra condition: no fully connected layers, absolutely no dense layers. Everything inside the fully convolutional neural network, which is also an FCNN, right? Weirdly enough. So the FCNN, or fully convolutional neural network, has an obligation that there is no FCNN in it, which is fully connected neural network, right? So the fully convolutional neural network is just a CNN that has an obligation of no fully connected neural networks. They both have the same acronym, but they are like extreme opposites. They're like the total most opposite things you could ever see. So when you see the word FCNN, always verify, is it a fully convolutional neural network or is it a fully connected neural network? Because you are talking about the absolute opposites of each other. So just having this difference is very important for your reasoning. In the quiz or something like that, I will always explain what FCNN I'm referring to. But in real life also, if you hear somebody say FCNN and you're like in the field of segmentation or in the field of, latent spaces or autoencoders, just always verify what kind of FCNN they're talking about. So a fully convolutional neural network is exactly an autoencoder that just has an obligation of no dense layers or no linear layers. You can see them, for example, in Keras. Or another representation is just no fully connected neural networks or no multi-layer processing, multi-layer perceptrons, right? So all of these words they mean the same thing. Linear layer in Keras, a dense layer in PyTorch, a fully connected neural network in general, or a multi-layer perceptron. All of them, they're kind of the same thing. But the most important thing here, fully convolutional neural network informs or makes us have this restriction that we should never ever use that kind of fully connected neural network. That's it. So all of these layers are just convolutional layers. Absolutely nothing else happening in this region. So I don't think we can go much in depth about the differences between fully connected 32 stride and fully convolutional neural network of 32 stride and fully connected, fully convolutional network 16 stride, fully convolutional network neural network of 8 stride, and the differences between them. But just to understand is,
I think the difference is pretty clear in my opinion. I mean, it's the fact that we're using much bigger strides, that we're just ignoring the boundaries more and more. This is what illustrated in the image, at least in a very intuitive manner.
Yeah, the stride here represents a much more complex concept than the stride of a one convolutional network. The stride here kind of represents the difference in size between the output mask and the input image, right? So when you see 32 stride, it means that the output mask is 32 times smaller than the input image. The 16 stride means it's only 16 times smaller. The 8 stride is only 8 times smaller than that. And this means basically that the 32 stride is much simpler to train, right? It's a very fast architecture to train. The 16 stride is a little bit in the middle, and the 8 stride is the hardest to train, mainly because it's much bigger and it will require a lot more training. So depending on how many samples or how many images do you have, you can train a different one of these different architectures. They're all the same, but it just tells you how many convolutional layers you will be using, how many max pooling layers you will be using. And sorry, for this one, it's the simplest to train. So if you have a small data set, definitely go for the 32 stride one. If you have a big data set and lots of annotations and lots of compute power, then go for a fully convolutional network of 8 stride. That's it, right? So the 8 stride just references to how much smaller the output pixel or the output image is compared to the input. As you see, there is no, what is it called? No upsampling it here, it's just convolutions. So the size always gets smaller, but you can say how much the size gets smaller, right? So in terms of, for example, concepts like max pooling, you can remove them. If you are using just convolutional layers, you can add some padding to make the output equal to the input. So there are lots of techniques that you can use to make the output of the convolutional layer a bit bigger, but every time you use them, you're introducing more computations. So just be careful about the 3 different versions. If you don't have a lot of data, go for the 32 stride. If you do have a lot of data and a lot of compute, then go for the 8 stride. And as you can see, clearly the performances get better every time the stride gets smaller, meaning every time the neural network gets more complicated. And this is the ground truth. As you can see, what ends up happening is, what you can think of it is every pixel in here or every pixel in here represents 8 pixels in the ground truth. And here, every pixel represents 32 pixels. And this is why it's very meshed together. And it's not good, right? SegNet is the like the first architecture that we will see that is pretty useful. So fully convolutional neural networks are important as a concept, and some people are even using them for classification directly from original input till the output. Everything is fully convolutional, but SegNet is something that is still being used till now. Like FCN is not very commonly used because it doesn't have good performances, whereas this one does. This one is very, very good architecture and a very, very beautiful model. And as you can see, it just has a couple of convolutional layers, simple, some pooling, very much expected. Upsampling, we have already seen that as part of the decoders, right? So remember, decoder is just upsampling with some convolutions, upsampling a couple of convolutions, upsampling some convolutions, upsampling convolutions, upsampling convolutions, and then this is the output. So softmax here is just used as a what is it called? An activation, final activation layer in here. That's it, because you have the segmentation output. If this was not a segmentation output and it was just a basic encoder, then you don't use the softmax. All good? For now, I hope so.
For now, yes. For now, yes.
There is another concept here that you guys are maybe not familiar with, which is batch normalization. And then pooling indices. Before we go to the pooling indices, let's speak a little bit about batch normalization. So as you know, neural networks are very, very volatile models. So if you're training a very basic multi-layer perceptrons, remember the fully connected model, and you have something like age, which goes from 0 till 99, and you have another thing that is like salary, which goes from let's say 500 rubles to somebody like a president or somebody like Elon Musk who make 9999999999999. So a lot of money. So you see the range of the word age, of the feature age, and the range of feature salary are very different. And if we train a neural network directly on these two features, the loss functions will get crazy, and the model will be, very quick to either, jump to weights that are not a number or jump to weights that are exactly zeros, which is not something that we want, right? So what ends up happening is the variance or the difference in variances between this feature and this feature makes the model highly unstable, which is not something that we want. So what ends up happening in even basic machine learning, it's not natural, it's not a neural network thing. So even in machine learning, basic machine learning, like linear models or support vector machines or decision trees, they also are very, very heavily influenced by the variance or the difference in scales of the variances of the different features. So what we do is normalization. So normalization is a very simple concept. So age becomes a value between 0 and 1, and salary also becomes a value between 0 and 1. So we just normalize this feature, and then we train a new model on top of these. And in the end, the model kind of learns a very good representation of these values, and there is no, what is it called? No explosion in the weights, no weights going into 0. There are not a lot of problems. This is what happens to the input. We normalize the input to make the model more stable, to make the loss function more stable. Somebody was like, why only normalize the input, right? So why just normalize the input? Why not normalize every single layer's output? And this is what they do. So the convolutional batch normalization combination is you take an input that is already normalized, right? Remember, input is always normalized. If you remember, let's just go to the lab and just show you guys. Here's the lab. This is the lab that we had before. Remember, every time we use any neural network, we always must use a normalization, right? As we said, all the models in the world require this normalization step just to make sure that they don't explode and they don't have like different preferences for these pixels or these features over the others, right? So normalization for the input is always happening. What ends up happening with batch normalization, or what we also do for batch normalization, it's loading. Okay, so what ends up happening with batch normalization is we take an input that is already normalized, right? We've seen that it gets normalized by default. And then after every convolutional feature map or convolutional layer, we apply an extra normalization for that specific batch. Even within the batch itself, after the convolutional layer, we apply some normalization. So just make sure that everything is between 0 and 1 again. Or another form of normalization is to make sure everything is between 0, -1, and 1. Just so that the values become more, controlled, so that the learning is more smooth. So this batch normalization technique is very commonly used in honestly every single model that you will see in the future. And it's this very simple technique that says normalization of the output of that layer on that specific batch. So every time a batch comes in, we normalize the output of that layer between -1 and 1. The trend between the features still is the same, but instead of one feature going to -100 and the other is just a very small range of differences, everything has the same range of differences and everybody is equal. So that is what batch normalization is. It just makes the training much smoother. The pooling indices are, as you can see, first of all, this layer in size is very similar to this layer in size, or the output of this layer is very similar to the input of this layer. Same thing in here, right? The size of this output layer is very similar to the size of this input. Size of this output is very similar to the size of this input. Size of this output is very similar in this output. To understand this better, let's go to the next architecture and see it in this shape of a U, right? So this shape of a U is much more useful because it allows you to see what is actually happening, right? So here, you take an input image, some convolutional steps. Again, it's very similar, like convolutional 3x3 ReLU, some batch normalization if necessary, some dropouts. All of these techniques are being used. You don't care about that. What you care about is this gray line in here. It takes, what it does is just copying, right? It takes the output of this layer and copies it as input for this layer. It takes the output of this layer and copies it as input for this layer. Takes this one, copies it to the next, take this one, copies it to the next. And if you have more, layers, it will continue doing the same. So what ends up happening is your encoder and decoder, they don't just communicate with one Z or latent space value. The communication between them is not only through the Z, but every layer in the encoder is communicating with its map or with its mirror in the decoder. This helps basically the map or the mask that we will predict to be more, you see this predicted mask? It just helps make the predicted mask more accurate. It removes a little bit some of the noises. Let me just here. Yep. Remember this? This is a very noisy mask, right? You see this noisy mask? It's very noisy. Even if you make the stride much smaller, what ends up happening is the model kind of forgets. After the model goes from this step all the way down and then comes here, kind of forgets some of the details of the input image. How can we solve this problem? By having these mirrored versions of the encoder and the decoder communicating together. So let me just split it here. Here's the split. This is the encoder. This is the decoder. And what happens is the mirror of every layer or every block in the encoder communicates with its mirror on the decoder side. This block number 2 in the encoder communicates with block -2, right? The block before the last, the second and before the last, the third and before last. So they are communicating with their mirrors just through a simple copy, right? It's a very basic operation, just copying and concatenating the outputs. So what ends up happening, let's just look at the, what is it called? At the trail that the input image will go through till it arrives here. So it will go through a couple of convolutions, some max pooling to make the size smaller, a little bit more convolutions, max pooling, also very similar concepts that you have seen before, convolutions and max pooling. So far, all is good. Up convolutions is just basically upscaling plus convolutions, right? So this is what up convolutions are, or deconvolutions, sometimes they're called. So here, all of this you have already seen before. If we ignore the gray scale, the gray parts, everything you have seen before is just a basic autoencoder. We improve its results by copying the output layer in here and merging it with the input from the upscale. Now the input for this layer is not just this, right? So usually what happens is layer 1 sends to layer 2 sends to layer 3, sends to layer 4, sends to layer 5. This is what usual architectures that you have seen before do. But now what we're doing is layer 1 sends to layer 2 and to layer -1, or the last layer. And layer 2 sends its results to layer 3 as before, but also to layer -2. So previously we had each layer sending its output to the next layer only. Now we have each layer sending its output to the next layer and the mirror version of it from the other side. As we said, this idea, although it's much slower, so it's a very slow idea, but it allows the model to focus on the details and provide more sharp segmentations, more sharp masks, more sharp, even if we were just doing autoencoders, just basic autoencoders and basic reconstructions, it will create much more sharp reconstructions. Basically, just by allowing the model to remember what was the input to it, right? Does that make sense?
Yeah, but I would say too many details to process, so that's why
Yes.
it might, yeah.
It's a lot. So the final step here, after we speak about unit, is the mask RCNN. So mask RCNN is not a really revolutionary idea in any way, shape, or form. It's just basically faster RCNN. This is faster RCNN. Remember faster RCNN? You take the ROI align, you take the input image, here the RPN is happening, region proposals, everything is going well. You have the region proposals in here. What you do is you take the ROI alignment. Remember, ROI align is a very simple, what is it called? Very simple operation that is basically reshaping this. It's like max pooling, but with this fixed output shape. This is the ROI pooling. So it takes the input, which could be any shape inside the image, and then maps it into the same size that we all require for every single object. It does the classification and bounding box regression. This is the part that we have seen in the object detection lecture. On top of that, it does an extra operation, very simple, just on top of it. For each individual object, it predicts a map. So mask RCNN is basically exactly like faster RCNN, plus a decoder that decodes the mask of the object. That's it. So previously you would just detect the bounding box of the object. Now you have an extra decoder like this one that is like added on top of faster RCNN to give you the prediction mask. That's all. This is mask RCNN. Mask RCNN is basically just faster RCNN plus an extra decoder that predicts the mask. A major difference between all of these, you see, all of these architectures is they don't see the individual objects, right? So this person and this person and this person, for all of these models, are the same thing. But for the mask RCNN, these different people have different colors. And that's the difference between semantic segmentation and instance segmentation. Semantic segmentation does the segmentation on the input image itself directly. You take the input image, you do the segmentation. Instance segmentation, on the other hand, what it does is find first the bounding box of each instance, and then you segment only that instance. And that gives you basically the segmentation plus the object detection. All good?
Yeah, to a certain extent, I would say.
We will see this later on in the lab in much more detail, and we will understand basically UNet a little bit more. We will see the code, we will see the copying, we will see all of these concepts. And we will see how we can do instance segmentation, which is basically semantic segmentation plus object detection. So instance segmentation is equal to semantic segmentation plus object detection. So I don't want to go into a lot more details. I think we should, we only have like 3 minutes left, so we can't really go into a lot more details for now. But hopefully during the next lectures, we will see segmentation in general. Semantic segmentation will be a very important part of the lectures. Instance segmentation will be a very small part of the labs, and hopefully we will also see how to build a simple diffusion model from scratch, right? So we will learn a bit about the theory of diffusion models. As we said, diffusion models is just basically a denoising autoencoder that is put on steroids. So we will be denoising like this, but instead of just one time, we will do it 100 times or 1,000 times. It depends on how our compute processes are doing. So let me just share the screen, for example. So exactly as we have seen before, you take the input image, you put some noise, you put some extra noise, you put some extra, now you can see it. You take the input image and you put some noise. If you're building a denoising autoencoder, you stop here, you go from this place to this place. That's it. If you're building a diffusion model, you will put these noising hundreds of times and thousands of times. Here it's very strong. As you can see, the difference between each individual step is very big. But in the actual case of diffusion models, usually the step size is much smaller. So basically here from this, when you take from this one to this one, it will take you like 100 intermediate steps. From this step to this step, it takes like 100 intermediate images, right? So this is basically what's going to happen in the next lab. Okay.
Okay, thank you for the lecture. Have a nice day.
Thank you, and I hope at least this was like some useful part for your projects. If you still have some questions about concepts like the latent spaces, GANs, or concepts like transfer learning and domain adaptation and how they use these latent spaces for different operations, then please just contact me directly and we can go through them. All good. Have a great day then.
Thank you. Goodbye.